So hello students, the next topic to discuss here is Z transform. So the Z transform can be regarded as the discrete counterpart of the Laplace transform in continuous domain. It is the discrete counterpart of Laplace transform. Let's say we have a sequence xn, a discrete sequence. Let's call it as xn. Now the Fourier transform for discrete sequence is given by this is called the discrete time Fourier transform representation for a discrete sequence or for the discrete time signals. Let's say we write xn, then it's discrete Fourier transform, discrete time Fourier transform. Let's call it as e to the power j omega. Now let us write a new term z or z equals to e to the power j omega. Now we can write a new representation x equals to x as a function of z equals to summation equals to minus infinity to infinity xn will be z to the power minus n. Now this representation in terms of z is known as the Z transform. Where z is any complex number. And this is in polar form. Now, if we take a more generalized expression, here you can see in this form of z, the magnitude of the complex number is 1. Now, if we take a more general form, let's say z equals to the magnitude of z, let us call it as r e to the power j omega. In that case, if we do the representation from here, then we can write x r e to the power j omega equals to summation n equals to minus infinity to infinity xn r to the power minus n into e to the power minus j omega n. We can give it as a more generalized form. So if we look at this equation and suppose if we write in terms of, or if you want to relate the Fourier transform as well as the Z transform, we can write as the Z transform is the Fourier transform of xn into r to the power minus n, and this will happen when r equals to, if you put r is equal to 1, or let's say we take z is equal to e to the power j omega. So we can call it as the relationship between the Z transform and the Fourier transform. If we write, if we represent the Z transform right here, it will be summation of xn z to the power minus n equals to minus infinity to infinity. This is the Z transform. So looking at this relationship, so this is the relationship between the Fourier transform and the Z transform. So this equation clearly implies that for Z transform to converge, the Fourier transform of xn multiplied by r to the minus n must also converge. This is the relationship between the Z transform and the Fourier transform for discrete sequence. Now we can define a new term here called the region of convergence. So region of convergence contains those points of Z for which the Z transform converges. It is region, or let's say regions in Z plane over which the Z transform converges. This is also abbreviated as ROC. let's take few examples. Let's say we have, let's take an example of a finite duration sequence. Let's say we take a finite duration signal given by xn. Let's say -1, 0, 3, 2, 5 randomly. Well, let's say 3 is the origin of the finite duration sequence. Now, if we try to represent this, it will be like the origin is at 3, then at n is equal to 0, similarly at t is equal to -1, n is equal to -1, and similarly at n is equal to -2. Its value is 3, its value is 0, its value is 1, -1, and similarly its value is 2 here, and its value is 5 at the points 0, 1, 2, -1, -2. So this is the discrete time sequence, a finite duration sequence. Now suppose we are interested to find the Fourier transform of the signal. Let's say the Fourier transform is given by x of z. It will be given by xn into z to the power -n summation n is equals to -infinity to infinity. And so we have got 5 points in this sequence: 1, 2, 3, 4, 5. So let's start with, it will be summation n equals to -2 to 2 xn z to the power -n. So the value of xn at n is equal to -1, -2 at n is equal to -2, so is -1 multiplied by z to the power n equals to -1, plus we are doing the summation. Similarly, this is the value n is equal to -2, and similarly this is n equals to -1 plus its value is 3 at n is equal to 0. Similarly 2 at n is equal to 1, and its value is 5 at n is equal to 2. So finally we can write, if we represent this in an ascending order, we can write 5 xz will be 5z minus 2 plus 2z minus 1 plus 3 that's it. So this is the Z transform for a finite duration sequence. So what will be the region of convergence? It will converge at all values of z except at, so we can write ROC belongs to all real values of z except at z is equal to 0. If you look at here, we put z is equal to 0, it will not converge. And at, we take very large value of z, so this is the case for a finite duration sequence. Now suppose we had, this will, it will not, if it's, suppose we had a, let's say a positive component of the z transform at z square, let's say at z square, and if z is very large, then this transform will not converge. That is why so these are the possible values. Now for this case, for this particular case, this will not happen because there is no positive power of z. Simply we can write for this particular case, this is a more generalized case, but for this particular case ROC belongs to R minus z equals to 0. Now that was the example for a finite duration sequence. Now let us take another example. This time we will take another type for a right-handed sequence. Let's say xn equals to an to un multiplied by un, where a is some value greater than 0, or it can be any value. Let's say, just for the sake of example, a is greater than 0 and un is step function. As we know, how do we represent un? And so on. So un equals to 1 for n greater than or equal to 0 and 0 for n less than 0. This is the unit step function, discrete step function. Now we are taking example of a right-hand sequence. So its Fourier transform x of z summation xn e to the power, sorry, not e, z to the power minus n equals to minus infinity to infinity. Now putting this value e to the power n z minus n. Now since this is a right-handed sequence, better we write summation n equals to 1 to 0 to infinity e to the power n z minus n. It will be sequence like xz equal to 1 plus az inverse plus az inverse whole square, az inverse whole cube, and so on up to infinity. So this is a infinite power series, and it's a form of a geometric progression. You can write 1 minus az inverse. It will converge to this form only when az inverse must be less than 1. Then only it will converge to this formula. So this will happen when mod of z must be greater than a. Mod of a for greater than 0, mod z greater than a. So this is the region of convergence for a right-handed sequence. If we try to plot this on the z plane, let's say this is the z plane where z equals to r to the power j omega. Now mod z represents the distance from the origin. So let's say this distance is mod z equals to a. Then ROC represent all those values of z, all those values of mod z greater than a. That means this shaded region it will extend up to infinity. This part is the region of convergence. Right? And you can see here, if you write the same, it will be like z upon z minus a. So you can see the region of convergence xz has a pole at z is equal to a and 0 at z is equal to 0. We can represent the same. Here we have the 0 and here we have the pole. Right? So one more thing to understand here is that the pole of Z transform does not lie inside the region of convergence, or in other words, ROC excludes the pole of Z transform. That is quite evident from the fact that ROC stands for the region of convergence. So pole can not be present over there. because the transform does not converge at the poles. That is why ROC does not include the poles. So this was the case of a right-handed sequence. As you can see, we took an example of a right-handed sequence. So we can see that for a right-handed sequence, the ROC is also outward and extends towards infinity, and it is outward to the outermost pole. We will summarize it. Let's take next example as now. Let's take an example of a left-handed sequence. Let's say xn equals to minus a to the power n u minus n minus 1. This is a left-handed sequence, and let's say the sequence is something like that. Let's say we have a sequence, and then this sequence will start from and so on. This is the 0, minus 1, minus 2, minus 3, and so on. So this is a left-handed sequence. So its Fourier transform will be given by summation xn z to the power minus n from minus infinity to the point minus 1. So if you write the same, you can write minus infinity to minus 1 minus a to the power n u minus n minus 1. We can remove u minus n minus 1 because we have already taken minus infinity to minus 1. So just put this as 1. You can write summation a to the power az inverse for n minus infinity n equals to minus 1. Now this can also be written as summation n equals to 1 to infinity minus of you can write az inverse minus n this is xz. Now if we write it will be minus taking from n equals to 1 to infinity a inverse z minus a inverse z whole square minus a inverse z whole cube and so on up to infinity. So we can write it here a inverse z upon 1 minus a inverse z. So this is the Fourier transform for a left-handed sequence, but this will converge only when a inverse z must be less than 1 for this to converge. For this, so it's ROC. Looking at this, relation, its ROC will be given as mod of z less than a. For a greater than 0, you can simply write mod of z less than a. So it points towards inward region for mod z less than a. If you plot the same on the z plane, you can simply write as, see, this is mod z, this distance is mod z equals to a, then our region of conversion is mod z less than a. All those values are mod z less than a. So this will be, so this shaded region is our region of convergence. And once again, it has got, once again it can written as z upon z minus a. The pole is lying over here and we have a 0 at origin. Once again you can see that the ROC is inward from the innermost pole. So we can see if the sequence is right-handed, then let's see, we have, if the sequence is right-handed, then its z transform will be given as same as 1 minus, we can write the same as, we write 1 minus, we can also write this transform as 1 by 1 minus az inverse. This is same as what we had got in case of the right-handed sequence. So whether it is left-hand sequence or the right-hand sequence, we got the same form of these z transform. The only difference is the region of convergence. So it will be 1 minus az inverse for mod z greater than mod a, right? And for left-handed sequence, xn given by minus e to the power n u minus n minus 1, xz will again be given by 1 minus az inverse, but for a separate ROC, region of convergence mod z less than mod a. Here the region of convergence is same, mod z greater than mod a. And so if we plot the region of convergence for mod z equals to A, the ROC is outward. It is outward to the outermost pole. If we draw the pole and 0, but in case of the left-handed sequence, this distance is mod z equals to A, and this is the pole, and this is the 0, then this will be our region of convergence. The shaded region, the green shaded region, it is our region of convergence. This is the z plane. So here ROC lies inward to the innermost pole. Here ROC lies outward to the outermost pole. In this case, we have got only one pole at z is equal to A. That is why it is always, or in case of right-handed sequence, it will always outward to the outermost pole. Suppose if there were multiple poles, like let's take an example. Let's say we have xz given by z upon z minus A and z minus B. There are two poles here, and let's say B is greater than A. In that case, suppose if we want to plot, we can see there are two poles A and B. Suppose there are two poles at A and at B, right? Then in that case, ROC must be greater than B for this must be the region of convergence, because ROC lies outward to the outermost pole. So let's say we draw the boundary point here at the outermost pole. This is mod z equals to B. So this will be the outer portion, the region up till infinity. It will be the region of convergence. It extends to infinity. Similar will be the case of, and suppose if we take the same example, once again we write z upon z minus A, z minus B. If this is a left-handed sequence, then if say A is, and for same B greater than A, then its ROC must be such that mod z must be less than A, because pole cannot lie inside the region of convergence. This must be very, very clear. So let's say if we plot the same, let's say this is our pole at A and there is a pole at B. So for a left-handed sequence, let's say this is the boundary of the innermost pole, then this will be our region of convergence. This is minus a minus b. No, this is not our pole. Sorry, I beg your pardon. Since we are taking mod z less than mod a, and all those point since we are talking about the distance, all those points on the boundary will form the pole of the transform. Similarly, if we take mod z is equal to b, all point at this boundary will form the pole of the transform. Now let's take another example. Let's say we have a combination, or let's say we have both sided sequence. That means, let's say, take an example, xn contains minus 5 to the power n u minus n minus 1 plus 1 by 2 to the power minus n u n. If we have, let's take this example, then this xn is a combination of both left-handed sequence and a right-handed sequence. So for the left-handed sequence, its region of convergence will be mod z less than 5, and for this right-handed sequence, its region of convergence will be mod z greater than 2, because this is minus in here. So the ROC will be, let's say this is R1, ROC1, and let's say this is ROC2. Then the region of convergence will be ROC1 intersection ROC2. So it will be 2 less than mod z mod 5. This will be our ROC for a both sided sequence. You can see that, and suppose if we plot the same, it will contain a ring. The ROC will be contained inside a ring. So let's say this distance is mod z equals to 2, and let's say this distance is mod z is equal to 5. This distance is mod z equals to 5. Now ROC lies between 2 and 5, then our region of convergence will be Now this form is a ring. And what will be the poles of the system? In terms of Z transform, if you write, it will be like, or separately if you write xz, it will be 1 upon 1 minus iz inverse plus 1 by 1 minus 2z inverse. So its poles will be at z is equal to 2 and 5, or let's say mod z is equal to 2 and 5. So these are the poles. Similarly, at z is equal to 5, this whole boundary forms the pole. Also of this transform. So you can see that once again ROC does not contain the pole. Poles are situated at the boundary of ROC or away from it. ROC does not contain poles anyway. So we can summarize here as the properties of region of convergence. First is very important point, ROC does not contain poles. Second point, for a right-handed sequence, ROC lies to the outer region, to the outermost pole and extends towards infinity. And for a left-handed sequence, ROC lies inward to the innermost pole and extends toward, just write towards origin. And for both sided sequence, ROC is contained in a ring. And last one, for a finite duration sequence, the first example that we had considered, ROC contains all values of Z except possibly except Z is equal to 0 and Z mod Z tends to infinity. Possibly we have used the word because the sequence is normally, for a finite duration sequence, is normally a polynomial. Then the polynomial may contain both negative powers as well as positive powers. So for positive, if positive power is present in the Z transform of the finite duration sequence, then the ROC will include Z equals to infinity. Same for the case if it contains the negative powers of Z, then the ROC will include Z is equal to 0. So we will continue our discussion. Thank you.